So welcome to the fresh episode of our story on photoelectric effect, and we are at a junction. So far we talked about these scientists working or doing experiments on the photoelectric effect, which Hertz accidentally discovered that yes, if UV light falls on metal, then it ejects negative electricity. Then Hallwachs confirmed that in his own way, and we almost reproduced that experiment of Hallwachs in this course. And then J.J. Thomson, who showed that the cathode rays in the vacuum tube and these electrons which are coming out because of this UV light, they are the same by measuring E by M. And then Stoletov doing some quantitative measurements on this photoelectric effect, coming out with the result that the current coming from this metal, that means the number of electrons coming from this metal, is proportional to the intensity of the light which is falling on that, like that. And then of course the great experiment by Lenard, where very carefully he makes measurements and comes out with an extremely important result that the speed of the electrons which are coming out of the metal does not depend on the intensity of the UV light that is falling on it, together with many other results that we had discussed. Now, in all these experiments that we have described so far, the focus was on the electrons which are coming out. So, if you have a metal and then light falls here, this is your UV radiation, and then electrons are coming out. Because of this, electrons are coming out, and these studies are basically focusing on the electrons. Electrons are coming out, how many electrons are coming out per second, what is that photocurrent, how it depends on intensity, what is the speed of these things which are coming out. These are same as that thing which comes out from the cathode in a vacuum tube. All these studies are focused on the electrons. Now Albert Einstein in 1905 focuses on the light itself. Develops a theory of light. What light is? What is the character of light? And how this light interacts with matter. Theory of that. Once that theory is formulated, then with that, what should be the characteristics of these ejected electrons? That he works out from the theory, and then shows that whatever experiments have been done, they are consistent with that. So this theory seems to be okay. That's the kind of thing. So the focus of Einstein is on the character of this light which is impinging on this metal, not on the electrons which are ejected. From that character of light itself, he works out that this should be the characteristics of the ejected electrons, and shows that yes, whatever experiments have been done, they are consistent with this theory. So let us today in this talk, in this episode, let us talk on light itself. If I go in details, it will take another series of many lectures on this light thing, because this history is also very old. In Indian context, there are several philosophies in Indian system, and one is Nyaya Vaisheshika. Actually, Nyaya is your logic, and Vaisheshika is the structure of materials and space and time, physical sciences, chemistry, physics, like that. So, and then later on, this Nyaya and Vaisheshika merged into one called Nyaya Vaisheshika. And there, a person called Vatsayan and others also, but prominently Vatsayan. And this is, I am talking of around say 600 CE current era. Okay, remember all these experiments are in 19th century. Okay, all these experiments are 19th century, and what we are saying is here around 600 CE. And there they describe what light is, what is the construction of light, constituent of light. And they are very interesting thing. They say that there is a stream of particles but not of atomic or molecular structure. In Vaisheshika, they talk at length about atoms and molecules and how atoms combine to form molecules and how different proportions of atoms, different kinds of atoms can make different kind of materials just by numbers. Okay, so there are elements and then different atoms, different materials will have different elements, will have different kind of molecules combined together to form molecules. So all that chemistry is there. What is the effect of heat? Heat will first dissociate molecule into the atoms, and then those atoms will recombine in some another proportion and another structure, and the material will have different properties. All those things are discussed in Vaisheshika in great detail. Although we don't find any reference to experiments, but somehow they have the conclusions or the description is available, is documented, is still available. They might have done experiments to reach these conclusions, but those are not available as of now. So they are talking of this thing means they know that light does not have that material particle. It's not like hydrogen, oxygen, nitrogen. It doesn't have a material particle. It doesn't have mass. But then yes, there is discrete small particles which makes this a steam, and then it goes with inconceivable speeds. All right, very high speeds. Then they talk of light or these light particles, going through interatomic spaces in the materials. So if you have glass or water, why it is transparent? Why light can cross through? Because in these materials they go through the interatomic spaces. So that kind of descriptions are all there. And where they don't find these interatomic spaces in good number, those things are opaque. So transparent, translucent, opaque, all these things. And if they reflect through the atomic surfaces, because if you have interatomic spaces, you also have atoms. So if light falls on the surface of that atom, then it reflects. So that is how they explain the phenomena of this reflection. So several properties are described in this. That is around 600. See, so it starts from there, and it gets changed every now and then, and newer things are coming. Still they are coming. People are doing excellent research on optics and so on. But I will mention here two things that we study as students. When we are in the schools, and especially in the lower classes, say class 8, class 7 or so, we are taught that light goes in straight lines. So from there, the chapter on light starts in our class 6, 7, 8 type of syllabus. Light, this is our schools, junior schools. Okay, and for that, the very famous activity which textbooks ask the students to do is to take 3 cardboards. Alright, not 2, not 4, 3 cardboards, place them parallel to each other, and then put holes in them, and on one side you have a candle and other side you have an eye. Okay, so this eye can see this candle flame only if the 3 holes are in one straight line, otherwise it does not see. So that's the proof, okay, that light goes in straight lines. And then talk of shadows. So if you have some structure somewhere, and then if you have a light source, then on the other side you have the same structure on this thing, shadow. This is shadow here, and then other places it is bright. But if the source had some size, then you have a lower intensity on here and more intensity here, and so on. And there are special names for it. In Hindi we call it prachaya, upchaya. Okay, and all those things are to show that light goes in straight lines. But when we come to college, what we are taught, light does not go in straight lines if there are obstacles like this or openings like this. Right? Here it is opening, rest is all open, and this is opening, small opening. Here rest is all open, and here you have some obstacle. So what we are told in colleges, once we come to class 12 or college, we are told that light does not go in straight lines. When they meet openings or obstacles. Okay, if you have a small opening here and a parallel beam of light comes, monochromatic, one color, what happens? Class 7 textbook will say that, alright, very good, you will have a bright patch here and rest all will be dark. But the college textbook will say that, alright, you have a bright thing, not of the same size, but maybe depending on this distance, maybe much bigger than this, so your bright can extend from here to here, possibly. Okay, so if a bright extends, that means perhaps this parallel beam becomes diverging beam. This becomes a diverging beam. So it bends. But still it goes in straight lines. But the more interesting thing is, this whole thing is not dark. You have dark here. You do have dark here, but then after that you again have bright. So the light is going in this direction. The light is going in this direction. Light is going in this direction. But light is not going in this direction. Light is going in this direction. The light is going in this direction. But then the light is not going in this direction. And again, light is going in this direction. Because this is bright, this whole thing is bright, and this is dark, and again this is bright. Okay, and then again dark, and so on. So the light is not going in this direction. Light is going in this direction. It's not going in this direction. It is going in this direction. So light splits in some very special paths. Of course, say whole thing is diffused like this. It's not just one line here around that, because you have bright from here to here. but then it chooses certain paths on which it likes to go, and there are certain other paths where it doesn't like to go. So those kind of things happen here, and we say that this is diffraction. Okay, so you have phenomena. A lot of scientists have studied that. It's a long history. If I go into that, I can give another series of lectures on that, the history of light itself, but I will confine to some specific things. So you have phenomena of reflection. You know the laws of reflection. You have phenomena of refraction, phenomena of dispersion. If you have white light and put a prism there, then it disperses in different colors. You have phenomena of diffraction. You have phenomena of interference. You have phenomena of polarization, and so on. Several phenomena. Speed of light. Now, this diffraction is very, very important for all these discussions on different aspects, and this was observed experimentally by one Italian scientist called Grimaldi before Newton, right? Grimaldi and Robert Hooke. So they actually experimentally found this and documented and told that the shadows are not sharp. The shadows are not sharp, and at the end of the shadow you have alternate dark and bright regions, and then it finally goes into the openings, the brightness. So those kind of experiments were done. And in fact, Grimaldi coined this word diffraction that we are using today, right? So that was the thing. Reflection, everyone studied. Refraction. Newton had done number of experiments on optics. That was late 17th century, and 1704. All right, 1704. He published all his results in this book, Optics. All the results, all those experiments which he has performed in several years, and then all the data and all the documentation and all the interpretation based on that was in this. In this he talks of reflection. In this he talks of refraction. In this he talks of dispersion. He talks of diffraction and also interference. He talks of polarization, although he himself doesn't seem to have done a lot of experiments on polarization, but another scientist. So this is Newton. And then you have this Huygens, Christian Huygens. He also writes a book on optics based on various experiments and various observations. And that was sometimes in 1690 or around that. Okay. Now the thing is that the same experiments, the same phenomena. When Newton described them, performed the experiment, describes them, then he describes everything in terms of those corpuscles, which are small particles. Light is made of small particles, right? That Wattsian description. So he uses this description, and with this description of this particle nature of light, he described this, he described this, he described this, he described this, he described this. Okay, and how he explains all this diffraction interference type of phenomena. He says that okay, the whole thing is in this hypothetical medium called ether that was prevalent at that time, and then this light, which are separately they are particles, separately they are corpuscles, small separate particles, but then they interact with this ether particle. That the material is different. Your mirror is a material, but an ether is still there in empty space, what you call empty space, air. Also in the between the air molecules also you have this ether. All that empty space is ether, and ether particles, they interact with light particles and they deflect it, and if you have a material, that material can affect that ether density close to its edge. And because away from the edge, the ether has different densities. So that different densities will put different pressures and this and that. That is how he somehow manages to describe these phenomena of interference and diffraction. Also in terms of corpuscles. And Christian Huygens, he also describes all these things, and that in terms of light itself is a wave. Light is nothing, there is nothing called particles of light, it is just vibrations in ether. Alright, just like sound is vibrations in air, of air molecules. Similarly, light is nothing but vibrations in those ether medium, and just like sound is propagating like a wave, light is propagating like a wave. And with that he explains reflection, right, refraction, that's very popular. Even today we use that Huygens construction of secondary wavelets. So he says that okay, if you have a wave front, you have the surface, and if light is coming like this, then that medium which carries all those vibrations and propagates that like a wave. So the same phase, particles vibrating in the same phase, that will make a surface, and that surface is called wavefront, and that will be perpendicular to this. And this wavefront will advance from here to here, here to here, here to here. So as it reaches this surface, this is, let us say, this is material. Okay, so this is wavefront, and this is light. And light propagates means what? Those vibrations which were here at in certain phase, now these particles or ether particles, they will be in that particular phase. So this wavefront has advanced. So that is how the wave is going, that is how the light is propagating. So that is the structure. Here you have particles, and the particles are just going like balls. And here it is those vibrations in that ether medium, and when it reaches here, then each point where it reaches becomes a source of secondary wavelets and all those things, and then the envelope of that, etc. That Huygens construction, we still use that very extensively. So with that he explains reflection, he explains light going in straight line if there are no obstacles, no openings, refraction, diffraction, everything, interference, diffraction, everything. And he also studied polarization, especially that what we call double refraction. There are some crystals like calcite. If you have a slab of that crystal, transparent crystal, put it on some page where something is written, and you will see from the top, you will see two images, not one. Simple glass slab will give you one image which is slightly lifted, and this will give two different images of the same object, just a rectangular slab. So it's called double refraction. That is because of manifestation of this polarization behavior which is in wave. So he does experiments on those and tries to explain with this wave picture. And since Newton writes his book later than Huygens, he knows that, and he comments. He doesn't give any explanation, but he comments that Christian's wave description of this is faulty. Okay, so those kind of things were there, and it was difficult to decide whether to go with the waves or whether to go with the corpuscles, because each one is explaining everything apart from this speed of light, which was not measured that time in the lab. Alright, in space we knew, but in materials we did not know. Prediction of speed of light, that was different. This wave theory of Huygens would predict that in a material, when light enters in a material from air, let us say, in glass or in water, its speed will decrease. Whereas this corpuscle theory of Newton will predict that it should increase, the speed should increase. But since the measurement was not there, so this was not the deciding factor, and other things were explained by each of those two pictures. So it was a choice. Some people favored this wave aspect, some people favored that corpuscle aspect. So one went with this kind of structure of light and some with that kind of structure of light, and that continued for almost a century. This is all late 17th century and just beginning of 18th century. But then this entire century, this debate was there. And then came Thomas Young, Fresnel, Fraunhofer, Airy. So these people performed experiments on again this diffraction and interference. So Thomas Young, and then Fresnel, and then Fraunhofer, Airy, people like and those experiments somehow tilted the balance in favor of this wave theory. And finally, when the speed of light was measured in the laboratory in water, then of course this wave theory won. Alright, so then it was fully established that light is not a stream of particles. Light is not to be seen as discrete quanta, one particle of light here and then another light particle here and another light particle here. Light has to be seen like a continuous wave. So that went on for another almost 1 century. Okay, when this experiment of Philip Lenard came in 1902 and Einstein came in 1905. So the very fact that the speed of electrons in photoelectric effect does not depend on the intensity, that was not matching with the wave theory as such, because if continuously light is coming continuously as predicted by this waves, then more energy falling per particle, per electron should bring that electron with more energy. But then Lenard does something and explain it. No, it's not light that energy is given from light to the electron. It's not like that. Light only triggers already existing energy in the electron to go out. With this much of energy, what are you doing here? You should go out and see how the world is. So light is making that triggering. That is how Lenard tried. But then Einstein comes with a very radical, very different kind of theory of light, and again going into corpuscles. Light has separate quanta. You can count. So that theory I will talk in the next episode and how it connects with the photoelectric effect.